This conference will now be recorded.
All right, fantastic. Well, welcome everybody to the fourth installment of the 4 training sessions that we have on understanding ecosystem metabolism tools in R. Kudos to you all for making it this far. We have a few less attendees than we started with, but that's typically how it goes. But majority of people are still here, so that's always good news. We've covered a lot today. We've talked about the basics of using R, how to use the detiding functions in weight reg DO, what are the basics of using the ODM metabolism method, and how to use those results to evaluate whether or not detiding has worked as you thought it would. And today, I thought it would be good to kind of conclude with just covering some basic tools that we might use to develop some more generic analyses around ecosystem metabolism. The great thing about SWAMP is we get all these other parameters that we could use to understand drivers of change or what's driving ecosystem condition in these estuaries. And so I want to explore some of the tools in the tidyverse that we can leverage to develop some of these hypotheses of what's driving metabolism. So if you're familiar with the tidyverse, this should all be kind of review at this point, but I have basically just some examples of how, at least in my mind, how I would begin developing some exploratory analyses with tidyverse using the results from weight reg DO, the metabolism results to describe that. So hopefully I'll get through all of that today. I've kind of in poor fashion run over my time every training session, so I'll try not to do that. But again, if you have any questions as we go, just let me know. Drop a question in the chat or just interrupt me as I'm talking. And as always, let's see. This is our tab for today. As always, we have this live coding link here that you can use to keep up with what I'm coding as we go. So you can refresh this page as I'm coding. Hopefully I'll be saving it as I go so you have the most up-to-date information and you can just copy and paste that information into your session as we go along. So I think everyone's familiar with that at this point. Either using local RStudio or the cloud version, either one works. But I think everyone's got a workflow now, so this should be old news at this point. Okay, so as I said, the goal of today is to basically explore some of the general tools in the tidyverse. In particular, I'm talking about using functions in dplyr, which is going to be your standard package with functions for wrangling data into different formats. I'll be talking about lubridate, which is a very handy package that comes with the tidyverse for working with date objects, and ggplot as well. So a lot of the plotting that we've done so far has been using some of the canned plotting functions that are available in weight reg DO. And those were developed with specific goals in mind to show you kind of a summary plot of metabolism, but they're not customizable, and ggplot will give you the tools as well as some of the other tools in the tidyverse to do these custom analyses as you want to do with your data. So hopefully by the end of this lesson, you should know how to or be able to find resources to basically summarize the metabolism estimates in different ways, how to make some plots with ggplot2, and then combining some of the metabolism estimates with additional SWAMP parameters to evaluate questions of interest of things you might think be driving metabolism at these sites. And then at the end of this, you should have, I hope, the building blocks for some more exploratory analyses on your own. That is my intent today. And obviously, in 90 minutes, we can't really cover the breadth of ggplot and dplyr and lubridate, but you should get a flavor for what you can do with those. And of course, there's links in the resources in this lesson throughout with further information on how you could continue your learning with these tools. So I'm going to start from a place where we basically have a data set that is something we've created in our past lessons. So I want to start with the detited data set for the Apalachicola dry bar station. If you go back to the detiting lesson, essentially what we're doing is everything up to the end of this and importing that data set. So I put this just for sake of saving time. I put a data set on the website that you can download that has that information. So this is an R data compressed binary file. If you load this in your current R session, you should have that file there. And so this is, again, going to be our combined water quality weather data set that is in the format we need for doing detiting and estimating metabolism. And if you remember from the detiting lesson, we run those data through the weight reg function and get output that looks like this. So your basic input data here, your water quality weather, and then output that you get from detiting. And so this DO normalized column is going to be your detited DO time series that you can use for metabolism. So we talked about how to get to this point with some of the other lessons, but this is where we're starting with, because this is, again, going to be something we can use to not only estimate metabolism, but use those metabolism results for more general exploratory analyses to figure out what's driving metabolism. So that's where we're starting. Just go back to the website so I know where we're at. Okay, so first thing we're going to do is use this data set to estimate metabolism. We're going to use the normalized time series, or the normalized DO time series there as input. So if you remember, we need essentially a couple key pieces of information about this site. We need the time zone from the date time stamp object in the data set. So this is a Eastern time zone without daylight savings corrections, which is pretty common for most water quality monitoring equipment. So that's the time zone, that's our latitude, that's our longitude for the site. And then we can start using the ecometab function from weight reg DO. And remember, we have to specify that we're using the ecometab function from weight reg DO because due to poor planning on my part, there is an ecometab function in Swamper that apparently does the same thing, but due to my laziness with updating both functions at the same time, the one in the one in weight reg DO is the most current one and has the most up-to-date fixes in there, or features rather. So input for this is going to be the APA detited function. We'll say latitude. It's going to be the latitude object there that we've defined above. Longitude is going to be longitude. TZ is going to be TZ. And then we have to specify what column in our data set is the DO column that we're going to use. And I can't for the life of me remember the names of the arguments of this function. So I will look at the help file. Okay, so DO var, we have to tell it that we're going to use the detited column. So that was DO norm. Okay, that should be all we need. We run that. And then we look at the first 6 rows. There we go. So we end up with an estimate for every day production, respiration, and then net ecosystem metabolism as the difference between the two. And these are all millimoles of dissolved oxygen per square meter per day. I remember correctly. All right, so now that we have the metabolism data, what do we do with it? It's great to plot it. We can use some of the plotting functions in ggplot, but maybe we want to explore some more kind of generalized plots. And so if you remember, there's actually there's a plotting function in the weightrec.do package that you can use to look at summaries. That's just the plot function here. By default, it gives you, I believe, quarterly averages. I'm sorry, monthly averages of the daily estimates with production in green, respiration in blue, and then NEM is the difference between the two. So that's great, but again, maybe we want to just look at production by itself or respiration by itself. So we want to learn how to use some basic plotting tools to make these plots on our own, which essentially we can use to reproduce a plot like this, but as we'll see later, we can use these plotting tools with some more general analyses or combining different data sets to look at what's driving metabolism. So I will give you a very, very quick crash course on ggplot, which is kind of like the de facto plotting library now in R. When I first started using R, I was using a lot of the plotting graphics in base R, which not quite as easy to use as ggplot and not quite as flexible. But now pretty much anybody who uses R uses the ggplot plotting libraries. And it's been around for over 10 years now, so it's pretty mature as a package, and it's got some pretty established routines and a lot of features that are useful for creating graphics. So we'll first load ggplot2. This comes with the tidyverse. So if you have the tidyverse installed, ggplot will already be installed. So all you have to do is just load that library, or if you load the tidyverse, ggplot will also load behind the scenes when you load tidyverse. So that's loaded. And then, what makes ggplot a little bit challenging for first-time users is that its syntax can be non-intuitive if you're not familiar with what it's trying to do in terms of setting up an architecture for creating your plot. And so I know many of you are probably familiar with ggplot, but basically the GG portion of ggplot stands for grammar of graphics. So it follows a grammar in a way that is a lot like kind of the parts of a sentence that fit together in different ways to form one cohesive unit of in this case, a plot. So you gotta understand those parts first and what they're doing to really appreciate the pieces and how they fit together in ggplot. And once you sort of wrap your head around that and become comfortable using it, you'll understand the powerful, or how powerful that structure is for building out the pieces of a plot in sort of a cookbook style approach to building these plots. But basically creating a basic ggplot is following a few simple steps at first. So every ggplot plot starts with a call to the ggplot function. So this is like the start of every plot. You call ggplot, and within it you say what data set you want to use. So here I'm just saying ggplot, make me a generic plot, but use the data set ABA eco, which is what we just created with our metabolism function. Now the next step is the part where a lot of people get lost conceptually, because it doesn't actually create the plot yet. It sets up how the variables in the data set are used in the plot you create, and this is called mapping. So you have to map variables in your data set to different plot aesthetics. And an aesthetic would be like what's on the x-axis or what's on the y-axis, or what is mapped to sizing or color in the plot. These are all visual elements of data in the actual plot. And so this next bit is basically just an expansion of telling it what data to use, but then mapping different parts of this data set to components you want to plot. So we use this function called AES, which is an aesthetics function. And it basically says map the variables in this data set to different aesthetic components in the plot. So here we're saying I want to map the date column in APA Eco to the x-axis on that component of the plot, and then map the production estimates of metabolism to the y-axis. And so this is the building blocks of the plot. You have the data and you tell ggplot what parts of your data that you're mapping to different properties or different parts of the plot that show aspects of that data. So when we actually run that, we don't actually get anything. We basically just get a blank coordinate system. So you can actually see that this is the start of the plot, and it has the components that we told ggplot to map. So we have the date variable on the x-axis. This is a date object in R, and so it knows that and it formats the values accordingly. So year, month, and then we have on the y-axis the production values from APA Eco. Now that we've set up the coordinate system for the plot, we've mapped the aesthetics to different parts of the plot, we can then set up what's called a geometry. And these are going to be the literal pieces on the graph you see: points, lines, box plots, histograms. There's, I don't know how many geometries there are, but these are actually going to be the literal features on the plot that show the data, actual physical structures on the plot. So then in order to build a geometry, like say we want to make a scatter plot, we just add the point geometry onto this base coordinate system that has the mapping and the data. So to do this, we use the plus sign, and then you do geom point. And so every geometry starts with geom underscore. And so you actually see right here how many there are for ggplot. And it really depends what type of data you have and what you're mapping to the aesthetics to determine what geom is going to be most appropriate or which one you want to use. But geom point, geom line are going to be probably the most common ones you're using. So if we do geom points and then hit that, we get the same plot, but now we actually have points mapped to our data set here. So that's your basic scatter plot with ggplot. I'm actually going to put this on the next line. That's a pretty standard convention for ggplot. You know, when you add pieces to it, you do that plus sign and then add a geometry or other pieces of the plot component on the next line. So maybe we want to add a line to this because this is a time series. So we could use geom line on top of that. So now we're making points in lines on top of the plotting system we've already set up. So there we go. So pretty straightforward. And again, this structure might seem a little overkill if you just want to make a basic scatter plot. But as if you want to learn more about ggplot and you want to get more comfortable about the different features it has, this construct of how the pieces fit together will make a lot of sense because it makes extendable pieces a lot easier to add based on how you set up the initial mapping structure. Are there any questions about that? Okay, so I'm going to assume that you guys have used ggplot before, because that could be kind of a tricky thing to wrap your head around if you've never been exposed to that. So again, this plot, the one that comes with the LaTeX package, basically uses ggplot under the hood to make a plot like this. And so I'm just kind of showing you the building blocks to make your own ggplots based on how you want to parse up the data. So I wanted to show you those pieces first because now, I'm going to start summarizing the data in different ways based on just, questions we might have about what's driving metabolism. And then once we do that summary, then we'll plot it to see if it sort of fits a general hypothesis we might have about what's actually related to metabolism. And now, we're getting into some of the other packages that come with the tidyverse. So the two that I use a lot are the dplyr package. Again, as I said in the beginning, this is a package that you can use for data wrangling, which will consume, a majority of your time in any sort of data analysis workflow. So all the functions in dplyr are very useful for subsetting different columns, renaming columns, joining data sets, filtering by rows, you name it. All of the basic tasks you have that you need to do for wrangling are going to be, for the most part, in the dplyr package. The other package is lubridate, which is a very handy package for working with date objects or date time objects in R. So why this is important is because dates are very tricky. There's sort of nested information from year, month, day, hour, minute, second, and how do you sort of pull out the different pieces, or how do you convert a character string or even a number that you import from Excel into a date class. And essentially lubridate gives you a lot of functions to do that. And so I'll show you just a few of them for summarizing the data today. Fortunately, with a lot of the functions in Swamper and WaitRegDO, when you do import the data and you're already working with it, the date time columns are already formatted as such, so you don't need to do that when you're importing the data. Basically, we're going to use lubridate on the back end to pull out like months or weeks or years from those pre-existing date time columns in the data sets we're working with. So what I want to do then is basically we have this metabolism time series again that shows the metabolism summary for the dry bar station every single day. So we have a date here from January 1st, 2017 to should be like middle of 2018 or late 2018. We can certainly work with these daily values if we want to retain values at that time step, but as we know, these metabolism estimates can be kind of noisy, whether it's due to, I guess, natural variation in the DO time series with changing weather conditions or whatever the caloric or the algae is doing in the system at that time, or even with tide, which can be a confounding factor. And so looking at the daily time step for metabolism could be less intuitive for evaluating overall trends than, say, a more coarse summary at like the month scale or the quarterly scale or even the annual scale. And so I want to show you how to do that using the tools in dplyr and with lubridate, because this might be something that you might want to do when you're summarizing data at your own site. So the first thing we need to do is basically take this date column and pull out some time unit of interest where we want to aggregate these data. And I usually like to start at month. I mean, that's the default plotting behavior for this plot, just because I think that, for lack of really diving into detiding and how well it can improve metabolism, the month will be kind of a nice summary of general trends. So we'll use two functions to do this. We're going to use the month function from lubridate and the mutate function from dplyr. And we kind of use them at the same time to create that new column. So you can see that on the website. Yeah, so I'll call it APA summary, because this is, we're going to actually summarize the metabolism data by month, but first we need to create that column. So mutate is a function in dplyr to actually make new columns or mutate a column from an existing column. In this case, we're going to mutate month from the date column. So we give it, again, our data as input, and then we're going to say, I want to name this new column Mo for month, or whatever you want to call it. And then we're going to use the date, or I'm sorry, the month function from lubridate to create this. But first, I need to load lubridate and dplyr. Again, so mutate is from dplyr. Month function is from Lubridate. So I run that line after I load my libraries. Okay. Oops. So now you see it's the same as before. We've just added or mutated a new column from date to create that month variable. And so it actually output month as an integer from 1 to 12. There's actual arguments you can use in here to output it as characters or an abbreviation for a month. But for this example, we'll just use integers. But now we have that. And so we can actually use this column to summarize the metabolism estimates to averages or medians or whatever summary we want to use. And to do that, actually, I think I'm jumping ahead. I wanted to show you a plot first of the monthly values. Yeah. So if we want to look at these monthly values, just in your workflow for evaluating the data, we can do that. So we can set up a ggplot just as before. We give it our data, as in this case, our APA summary data set that we just created. We're going to use the aesthetic function to map, in this case, month on the x-axis. So x equals mo, and then in this case, we'll do on the y-axis production values just as before, except now we're using month instead of date. And we actually have to add another aesthetic in here called group, which basically says group the values by month, because if we don't do this, ggplot will think the month values on the x-axis are continuous numbers, and you'll get wonky, you get one massive box plot. It's just sort of a weird peculiarity of ggplot with number values on the x-axis. But once we set that up, so again, this is, if we do this, it'll just create that base plot that has the different variables mapped to the aesthetics on the plot. But then we can add our geom box plot on there. And so this, again, just will give us a nice summary of medians, quartiles, maximum, minimums, outliers of production by each month. So that's one way to look at it. But maybe we want to go a step further and actually like calculate these things on our own. Like maybe we want to actually calculate these mean values or these median values for downstream analysis, which we'll actually do in a little bit. So we can use some other functions in dplyr to do this. And the two other ones we'll use today are, there's the group by function and summarize function. And this is just the step you have to go through to summarize data. You can say I have to basically set up a column that I'm going to use as my grouping variable. In this case, we're going to use month. And then when we summarize, we can summarize other columns in that data set conditional on that grouping variable. If we don't do that, we'll just get a summary for the entire data set that doesn't have some sort of grouping variable. So let me just make sure where I'm at in my workflow. Okay, so these, yeah, it's these two functions, group by and summarize. These are, again, two things that come with dplyr. And since we've already got our month column set up using lubridate and mutate, or month and lubridate, we can group by that column and make those summaries. So I'll do that right now. So I want to overwrite APA sum, but I'll first set up my grouping variable. I'll do it on APA sum, and I'll say I'm grouping by mo. So when I run that, I look at the first 6 rows. It's the same data set as before, but now that's not right. I think I need to let me create that again. Oh yeah, it's because I put the wrong argument. All right, well, I'm gonna look at the help file because I've forgotten the name of that argument. I don't think you need to specify it. Okay, so basically I was just reminding myself that to group by columns, sorry folks. Okay. Okay, so I was incorrectly trying to specify an argument for the grouping variable. It's basically just the names of the columns you put in there without specifying an argument name. So this APA sum object, I had to recreate it again. I kept adding variables by mistake using the group by function incorrectly. But essentially, this group by function, it doesn't do anything to manipulate the data if you do it correctly. It basically then tacks on an attribute at the top here that basically is something that dplyr knows when you do these summarize or mutate functions to run the analyses by a conditional column in your data set. So now we have basically the month column as a grouping variable for these downstream analyses. So if we were just to look at the original data set, we see that there's no grouping variable up there. So we have to first define that. But then once we have that grouping variable set up, we can use the summarize function to basically summarize any column in this data set by the grouping variable. So I have APA sum as input. And in this case, I'm going to say, I'm going to get the mean production. And so I name that column whatever I want, mean PG. And then this is the function that I write to summarize it. So I say I'm going to take the mean of PG. And if you have been using the mean function before in the past, you have to specify what to do with missing values, or else you'll get an NA value for anything that has an NA in there. So essentially, we can run that and look at that. And now we have all of our production values averaged to each month. So very powerful thing to do with dplyr. You can add any other thing on here. So if I wanted the mean respiration, I could just do mean RT ARM equals true. Or I want max NEM, I could say take the max NEM equals true. So you can add on anything there that you like. So yeah, that's just a very quick and simple way to summarize the data. Now that we have that, we can obviously plot that or combine it with other data sets that are maybe collected at the monthly time scale. And that's kind of the utility of doing that. So I'll close with basically showing you making a plot of the summarized data. So X equals month, and then Y equals, we'll do mean PG, and then we'll add geome point on there, and then a geome line on top of that. So again, it's a coarse summary of this information, but it can be useful if you want to pull out central tendencies of these data or any other summaries for plotting or combining with other data. So does that make sense to folks? Did I go too quickly through that? Okay, solid. So glad people have their cameras on today. So I think that's it. Okay, so for I'll put 5 minutes on the clock, and then we'll go through the exercise, but essentially I want you to do the same thing. but with the Sapelo Island data set, the detitled data set from last time. So you could load this from a pre-saved data set on our website, so we don't have to go through all the detiling from last time, but you can load it, run metabolism using these parameters, add a month variable using mutated month from Lubridate, get a summary grouping by month of mean production or respiration or whatever you want, and then plot the data and see if it looks interesting or if we did it right. So I'll put 5 minutes on the clock and we'll talk about it afterwards. All right, so I realized that's a lot of stuff to do in 5 minutes. So I put the workflow on the live coding link, so you can check that out. Essentially, I'll just pull that over here. So it's the exact same steps we did with the dry bar site. So loading in the data here on line 336, specifying the time zone, Latin long for the station, using the metabolism function from weight_reg_do, specifying that we're going to do this on the dtited column in SAP DTD, and then doing the rest in dplyr, lubridate, and ggplot. So adding the month column with mutate and month, grouping by that month variable, summarizing by that month variable, but taking the mean production, making sure we handle the NA values appropriately, and then finally creating a time series plot from those data. So I put these on here, not just to show you what the exercise is doing, but we'll actually be using, I believe, both of these SAP ECO and SAP sum objects in the next exercises. So when we do get there, make sure you've run this code so you have that. Any problems with that? Questions about that? All right. Again, fire hose of information here. I feel like I'm going through this really quickly. I just want to point out a few things. Shannon and others have mentioned in the chat that there's, excellent cheat sheets available by RStudio that is like a nice little summary of how to use some of the more common functions in each of these packages. So check those out. I've also got them on the data and resources tab of the web page if you want to use those for follow-up learning. So now we're going to get into the fun of actually combining SWAMP data with some of our metabolism results. So as I said at the beginning, the value of SWAMP, or one of many values actually, is that we have all of these other parameters that we can use to describe the system and also maybe describe what's driving metabolism. And so we can kind of generate some reasonable hypotheses of, well, maybe temperature is driving metabolism. It's one of the few things that could drive it, because as the warmer months come on in the growing season, there's more biological activity in the system, more algae being produced, and you can see that reflected in the DO time series. And so maybe we want to relate temperature to production, for example. We can do that in a number of ways. We can pull in the SWAMP data with existing tools in Swamper. So we've talked about in previous exercises using the import local function to pull in the data from scratch, the QA/QC functions to clean up the QA/QC flags, the combine function to combine data from different sites, so weather data and water quality data, for example. I'm not going to review those because we actually have a starting data set that already has some of those data combined, so that dtited data set for dry bar that we imported in the beginning has some supplementary data set or variables in there that we can use to compare with metabolism. So we'll start there. So again, we have our let's see, combining eco-metabolism with SWAMP. So we have our APA dtited data set. We'll start there. We have like water temperature, salinity, air temperature, pressure, wind speed, tide, all that fun stuff we can use to combine and compare with metabolism. But if we look at our metabolism data set, we have data at the daily scale. So we have an estimate for production, respiration, NEM at every single day. But looking at our water quality data, this is something that we've imported and created to have observations at every hour. So how do we combine these data sets in a meaningful way to actually say, look at how temperature relates to production or respiration. Well, we can use a lot of the same tools that we used in the last lesson, where we can group by a particular variable, take an average of, say, temperature within a day, and get those estimates down to a time scale that then we could use for comparison with metabolism. So that's what we'll be doing. So I have, as a first step, we're going to summarize this APA DTD data set to take average water temperature within a day that we can then compare to metabolism based on some hypothesis that we'll develop about the relationship with production. So we'll use APA sum again, or we'll just rename or use that name again for the variable. We'll use some tools from dplyr. So we have to make this date timestamp column a date object. So we have to say, I'm going to make a new column, and I'm going to say date is going to be date function, date timestamp. So this is the same syntax before. We're just creating a new column. We're naming it date, which is kind of confusing because we have a function called date. That's usually not good practice, but we'll just ignore that for now. And essentially, we're just taking this object here that has date and time, and we're just pulling out the date from that. And so this is a function from LubriDate. So we'll do that. We'll look at that. APA sum. So now it's the same as before again, but we have this extra column on the end here that has a new set of values that just shows the date. And the value of that is we can group by that column. Okay, so now remember, this is the same data set, but we have the date column as our grouping variable, and we can summarize by that. So we'll summarize, in this case, say we'll take the mean water temperature within each day. So we'll say mean temp equals mean of the existing temperature column, deal with NA values accordingly, and then run that. And there's our summarized data set. So we basically drop everything that wasn't summarized, and we retain the summarized values for the things we told dplyr to summarize at the level of the grouping variables that we've told it to group by. So every day we have an estimate of mean temperature. So now we can actually combine this with the metabolism estimates to maybe see if there is some relationship of temperature with our various estimates we have to describe metabolism. So if you remember, was it 2 lessons ago, or maybe 3 lessons ago, I talked about the combine function in Swamper, which is something you can use to combine different data sets by dates using the same date column as your joining factor. There are actually some generic join functions in dplyr that do exactly the same thing. And quite honestly, if you learn how to use those, you'll be much better off than learning just how to use the comb or combine function in Swamper, because they're extendable to any sort of data set in R. So we have a whole suite of joining functions in dplyr, left join, right join, inner join, full join. It all just depends on how the data sets are overlapping by the key variables that you want to join by. And so in this example, we're actually going to join this summarized data set to the metabolism data set based on an inner join, which says join all of the rows in both data sets that only share values for that same key. So if there's a day in metabolism that isn't in the water temperature summary, it won't join that column. Or if there's a day in the temperature summary that's not in the metabolism data set, it won't join. It will only join by days that are shared between the two. And that's because we want to basically look at the relationship between temperature and metabolism for days where we have both of those values. So in this case, an inner join will make sense. So I'll set up APA join, and I'll use the inner join function, which is from dplyr. And the first two arguments are going to be the two data sets you're joining. So APA sum and APA eco, and then the joining column, we'll call that date. And actually, what I need to do is rename that. So in order for you to join two data sets, they have to have a column that shares the same name. So if we look at how I've set this up, so APA sum here is date lowercase, and APA eco has date and uppercase or title case. So I need to rename this date column for APA sum. So I'll just do all that over again. So now you look at that and verify, okay, now it has the same name. Otherwise, if we don't do that, this function will tell us that we can't join by variables that aren't shared between the two, all that fun stuff. So let's join that, inner join. So again, this is combining rows where the dates are shared between the two. So the days that are both the same between the metabolism and summarized data set. And there we go. So it's combined. So there's our joining column there. Here's our mean temperature column here, and then all of our estimates for metabolism all in a nice tidy data set here. But then now that we're on the same data table, we can actually look at comparisons between them. And of course, there's a lot of ways you could do that, but for this example, we'll just look at a simple scatter plot. So we can go back to our ggplot function here. In this case, we're going to use the data set we just evaluated. On the x-axis, we'll do mean temperature because this is our independent variable that we're sort of hypothesizing is related to production in some way. And then we'll do y as our dependent variable. We'll do PG. That's set up, and then we could add a geom point geometry on there to actually make those points. So if we run that, we get a scatter plot. And not gonna lie, when I was making this exercise, I was hoping to see some of a relationship there between the two, but it's just not there. Could be for any of a number of reasons. Maybe anomalous production values, maybe that this time scale we're looking at, those two things aren't related. Maybe there's a lag in time between the two. Who knows? I just kind of want to show you how to make these broad summaries of the data. Is just develop your own analyses in-house. So that's kind of the goal of this, but you know, you can kind of get a sense for how that workflow goes. You got to think about what are the things you want to compare. How do you get them on sort of a temporal scale where you can start combining the data sets, and then once they're combined, how do you look at them to say whether or not this relationship meets your hypothesis of whether or not these two things are related. Any questions about that? All right. So you probably guessed it, the next exercise is going to be doing the same thing, but with the Savilo Island data set. And I haven't actually looked at this example yet to see if there is a relationship. So I'll be pleasantly surprised if there actually is, but I'll put 5 minutes on the clock, and then you'll take a stab at it and we'll reconvene afterwards. So Sapelo Island never fails to disappoint. There's actually, I doubt this is a significant relationship, but I do see a somewhat positive association between temperature and production. I mean, super weak, but at least it's in the direction that I would expect. So that's kind of cool. But I've put the answer here in the live chat. So again, same workflow as before. Create the date column, group by that column, take the mean temperature to get average temperature within each day, and then use an inner join with the metabolism data set and make a plot. And actually, if you aren't familiar with Geom Smooth, this is kind of a handy tool to make trend lines on ggplot. And so this is actually kind of the nice, one demonstration of the nice flexibility or extendability of ggplot, where, you know, once you have the aesthetics set up in your base plot, you can add any of the number of geomes that use those same aesthetics. So in this case, we're just saying, you know, not just add points to X and Y, but make a smooth line of essentially Y versus X, just like you would for any regression. I have seen this geometry abused for people just sort of put a continuous nonlinear smoother on any sort of scatter plot and sort of say, hey, there's a relationship. And so that's kind of the downside of these types of things, where it's really easy to add a trend line, but doesn't mean it necessarily means anything in terms of actual ecological relationships. But in this case, it's just sort of a nice tool to do these exploratory analyses. So the last bit of stuff is kind of like the exact same thing we just did, combining other parameters from SWAMP with metabolism estimates to look at potential drivers of metabolism in our system. And so I wanted to look at the nutrient data because this is a special case where these data are not collected, or they're not stored in the same data tables as water quality data. So there's an added level of complexity there with how you want to combine that information. But even more importantly, you know, the nutrients would be probably your number one hypothesis of what's driving production in the system. So, I mean, depending on where you're looking and what else is going on at your reserve. But by and large, you know, like nitrogen, phosphorus, or chlorophyll exactly would be maybe a direct surrogate of production that you can use to compare with your metabolism. So I wanted to go through this example to show you how to start doing those comparisons. And then unfortunately from this one, we need to start with import local because we don't have, we've actually not worked with the nutrient data from SWAMP before. So the data project folder, or the data folder you have for this training that you downloaded, has a whole slew of files. So basically every water quality and weather and nutrient site at Lechicola and Sapelo Island are in here for 2017 through 2019. And so again, this is something we've downloaded with the advanced query zip downloads feature of CDMO, because that's something that import local works with. So this is meant to emulate a folder you would download from CDMO, and then that plays nice with import local. So we're actually going to import the nutrient data from dry bar station. So we'll load Swamper. First, I'll say combining ecometab with nutrients. All right, so import local. Remember that one takes the path to where the data are. In this case, since we're in a RStudio project, the path is relative. So this is our data folder within our root directory, which is our home directory for our project. So it's in the data folder. Our station code is going to be APADB net, and then it should work. Okay, and then we just get a little warning to say that, you know, this is not basically water quality data. That's fine. But now the next step is, remember, we got to use QA/QC to deal with the QA/QC columns and maybe filter values out that don't meet flags that we want. So this is the data we just imported. So we'll use QA/QC, APA/DB nut. QA/QC keep is going to be the argument we use to keep values for flags that we care about. And again, this is up to your choosing which flags you want, but these are going to be, I don't know if I'd call these a standard set of flags, but ones that are pretty liberal in terms of what they keep. So all of the positive integers, including 0. So there's that same thing, you know, we just remove the QA/QC columns and filtered out values so don't meet those flags. And we have data for 2017, 18, and 19. So it pulled in 3 files to get this. So there's the last 6 rows there going through 2019. So what's unique about nutrient data is that these are basically collected once a month or twice a month, I guess, depending on where you're at. But basically, you know, these are, you consider these kind of like daily values, basically. And in order to combine them with the metabolism data, we need to do 2 things. One, make this date timestamp column into a date, because we don't need the time of collection for this. We want to just say what's the date of collection. And then because we have the metabolism estimates at the daily scale, we can kind of slice out the days in the metabolism estimates in the same days where we also have nutrient estimates. And that we can accomplish with an inner join, where we're saying combine the 2 data sets, but keep the rows where the date is shared between the 2 data sets. So again, this is very easy to do with dplyr. We don't actually even need to do any group by or summaries for this. We just make a date column for the nutrients and then do that inner join. So we'll do that. I'm going to make, what am I calling this? I'll call this APA summary again. And we're going to make a date column for date timestamp, because we can't, again, we cannot join this column with the date column in the metabolism estimates, because 1, this isn't a date yet, it's a date time object, and 2, it doesn't have the right name. It's called date timestamp and not uppercase date or title case date as it is in the metabolism estimates. So we'll say I'm going to make a new column, call that date equals, and use the date function from lubridate on the date timestamp column. Run that. And again, same data set, we've just added a date column. So now that we have this, we can use that inner join function from dplyr to basically join by this column, and we're only going to get essentially all of the nutrient data and only the days where we have metabolism estimates that correspond to the same days where we have nutrient data. So we'll do APA join. And I also, you know, before, with an inner join, it doesn't matter which data set you put first, because you're just taking the intersection between those 2. If you were doing a left join, for example, it would matter which data set you put first. But for now, you can do APA sum first or APA eco first. It really doesn't matter. You're going to get the same rows because you're just combining by shared dates. And then by equals date. Okay. So we'll look at that. So there we go. So we have our nutrients data. We don't need that date timestamp column anymore, but it's there. We have our date column, and then the metabolism estimates that share those same dates with the nutrient data. and vice versa. So now we're ready to make a quick plot. So we can make a ggplot again. We'll say we'll use the data as our data set we just created. For this one, I'm going to actually do chlorophyll, since this is going to be like the state variable that is maybe most closely linked to DO. So I'll put that as the independent variable, and then the dependent variable, I'll use production again, and then I'll do genome point, make my scatter plot, and change that to Y. So super disappointing plot there. I don't know what that's telling me. Basically, that's telling me nothing. But other locations, other data sets, you might see a relationship. And in fact, I would go so far as to say that this lack of a relationship here is probably the exception rather than the norm. I just have a growing hatred for data at APA because it doesn't conform to my half-brain hypotheses. But anyway, that's how you would create that scatter plot there. And this is just a really coarse analysis, you know. Just because an instantaneous measurement of chlorophyll at one day doesn't correlate to a daily estimate of production at the same day, doesn't mean those two things aren't linked. There's other ways you can look at the data. Maybe you do a seasonal parsing of the data. Maybe you aggregate at different time scales. Maybe you do a lagged correlation. There's a lot of ways you could do it, but this would be like your starting point for how to do it. So as kind of a next step to that, you know, you could say, well, we're not seeing this instantaneous correlation between the two things. Maybe I want to evaluate the data a little bit differently. And so a lot of times, you know, what I'll do is going back to this idea that these daily production estimates can be quite noisy. Maybe, for example, I want to compare nutrients to monthly averages of production instead of these daily averages. And that could be maybe one attempt at trying to reduce some of the noise in these relationships, because maybe it's just this mean production value that's a more accurate characterization of this more general trend we see in the data. And we might expect that to increase or improve the relationship with some of the nutrient parameters and the nutrient data set. So let me just make sure that's what my plan was in terms of telling you what to do next. All right, there's our plot. And you could actually, yeah, you could put any of the nutrient parameters on the x-axis or any of the metabolism parameters on the y-axis and see if there's a relationship there. That could be another way to evaluate the data. But as a last example, I'm going to show you how to do like this general summary of averaging the production values at the monthly scale in a kind of convoluted way, using a new function in Lubridate that we haven't talked about yet called floor date. And I have my reasoning for using that. Hopefully I'll explain why in a clear enough way that it makes sense. But essentially we want to, again, just take the average metabolism estimates and join those with month. So let me introduce you to the floor date function, then I'll try to explain why we're doing that. So let me just copy that. So we're going to create a new column in the metabolism data, in the nutrient data, that is a date value floored to a particular time period. So these nutrient data, again, we have this date time column, but we maybe want to compare these to average metabolism values at the same monthly time scale. So we have this floor date function where we can create a new date column, but it basically takes this date time object and floors it to a common value. In this case, we're saying turn this into a date, but floor it to the first of the month. I think there's also an analog called ceiling date where it would be make the ceiling the last day of the month, but essentially when we run that, What is the problem? It's my favorite error. Because I've got the wrong variable in there. There we go. So when we look at that, now essentially this date floor column is going to be every single date time object, but now to the first of the month within the month that date timestamp was collected. So this is January 1st because this was collected in January 2017. This is February 1st because this is February 6th, so on and so forth. Now we can do the same thing with the APA Eco data set. Date floor. Again, I'm just naming this column whatever I want to hopefully describe what I'm trying to do. If you did week, for example, you could floor it to the closest week, or year, you could floor it to the closest year, or day, the closest day. This is actually a really powerful function for changing the date. And actually, it can be kind of dangerous because you are changing the date at which something was collected, but you can kind of cheat. And actually, this is the reason why I'm using this. You can kind of standardize disparate things connected at different points in time to the same date for the purpose of combining information. In this case, we're aggregating to the month scale. So it's useful to floor the date time to the month value. So everything, the dates are the same values and the nutrient data as they are in the metabolism data. So we can group by those and summarize by those same floored dates, but then we can also combine them to the same floored date. So we can combine them in a way that they're actually reflecting a similar timestamp, even though, again, we are sort of changing the actual point in time in the data set that says when these things were actually collected. Does that make sense? Or am I just like sort of going in circles on that? All right, so because we're doing this analysis of the monthly scale, it doesn't matter what the day is in the month, is essentially what I'm saying. We can just sort of floor it by that, take the summary and combine to get them on the same time scale. So that's my whole rationale for doing that. So run that again. So what is going on? Oh yeah, so this is dates in this one. So there's actually a date column in APA Eco we want to use. So now we have, you'll see that everything in January, in this case, for the metabolism is now, this date floored column is now in the first. And we have a comparable column in the nutrient data that we can use to combine when we're ready to do that. So in order to combine them, we would want to summarize the metabolism values by month. So the floored date value, so this column here, because we have only one observation floored to month in the nutrient data. So that way we can then compare kind of apples to apples using aggregates that make sense at the monthly scale. So we'll use our friend group by and summarize APA DB9 group by the floored date. Then we will summarize. I'll do mean PG again. Mean PG, deal with NA values. Oh, sorry. We'll do temperature. This is sorry, this is the nutrient data set. Or I'm sorry, I will do chlorophyll. My data set's mixed up. Okay, so that's chlorophyll. And actually, we didn't even need to do that because the data already, one observation per month for the nutrients. So what I should have showed you is how to do that for the metabolism estimates. So we'll group by date floor again for those. Then here we'll do mean production. Okay, so now you can see what we're trying to move towards. So we have both of these things with essentially one observation for every floor date here that we can combine by the shared column date floor, so we can compare chlorophyll against mean PG, again, as a way to try to reduce some of that variation we see in the metabolism estimates to the monthly average. So let's run that again. Let me just make sure. Already overwritten my metabolism object. All right, so now we can just join them by that date floor column. So we use an inner join, again, to join only by the dates that are shared between the two. PA sum by floor. Okay. So now we're ready to make that scatter plot with our hope that by taking the monthly averages of metabolism, we've maybe reduced some of that noise and possibly improved the correlation in our data. So ggplot again, mean chlorophyll on the x-axis, mean PG on the y-axis, and then make a genome point. And then look at that. And so still doesn't look like much to me. It's certainly not quite as wonky looking, I guess, but this looks like a shotgun blast to me. So I could maybe say that at the monthly scale, chlorophyll doesn't really seem to be related to production at this site. Again, doesn't mean that chlorophyll isn't related to production at all times of the year across all locations in Apalachicola. It's just this simple course analysis we've done. And how we've manipulated the data to address this very simple hypothesis doesn't suggest these two are linked at this point. And I'm going to cross my fingers and hope that Sapelo Island does show a relationship when we do a similar analysis. So I will put 5 minutes on the clock. And again, just to respect everybody's time, we're actually at 2:30. We're 2 minutes close to 2:30. So if you need to go, by all means, don't feel free or don't feel like you need to just stick around. But if you want to stick around, I'll show you how to do the exercise when the 5 minutes is up, and we'll just entertain any other final questions you have about working with these packages.
You gotta run. Got another meeting. See y'all.
All right, Dave, thank you so much.
And folks, remember, you can ask me questions if you have trouble.
Yep, go to Dave first, not me. All right, so last exercise, hopefully be able to make some progress on that. Again, I know 5 minutes is really not a lot of time to do that, but you can basically just copy and paste all what I've got so far up here and replace the names of the stations with Sapelo Island stations and get to the same result. So again, we're just sort of importing the nutrient data, cleaning it up, adding a floor date column to both the nutrient data and metabolism data, summarizing both to get an average. It doesn't really make sense for the nutrient data since it's only one value per month, but for the metabolism data, you're just taking an average of all the days within a month to get mean production or mean respiration or whatever you chose. And then we're joining the two by that floor date and making a plot. And unfortunately, this didn't look like there's much of a relationship of chlorophyll with production at this site. You know, if I'm looking at this, maybe it's that, oh, it's these outliers that are driving this correlation down. But if you squint, you're like, oh, maybe there's a somewhat of a positive correlation. So that could be suggestive of something. But again, this is all just kind of exploratory stuff that you can do to sort of ask different questions of the data, what's driving metabolism. Again, leveraging the existing data in SWAMP to let you do that. So that's all I've gotten for you today. And actually, that's all I've got for you for the immediate future. I really, you know, I hope you guys got something out of these trainings. All the recordings will be online. This website will stay online as long as GitHub exists as a resource for you all to go back to and learn how to further your skills. But I hope this was useful for you guys. It's been fun for me to do this. I'll be a resource if you want to get in touch. This is also just a reminder, this is part of that bigger NSF project that we're working on with Ray Nadger, Wade McGillis, Jill Ariola, and Maria Herman, all at Penn State and Columbia University to understand how we can use metabolism to make better inferences of what's happening at these sites and using NERRS as a test bed for all of these products. So I fully expect maybe towards the end of this project, maybe in a year or so, we'll have some more trainings with additional tools as they're developed, hopefully improved tools. And yeah, you can look forward to that. So if there's any questions, comments, I could take some now. Otherwise, thank you all for sticking on.
I have one question.
Yeah.
And it's mostly just I would like to phrase the floor date or how you approached the average in a different way I would do it, and make sure that, like, I think I understand why you did it, but let me just phrase it and see if what my brain makes sense. So could you approach how you combined everything using the floor date by instead just making a new column that's month year instead of flooring it to like the first of each month and then just group by that month year column and average? Would you get the same result essentially?
Yeah, you absolutely would. That's one way to do it. The only disadvantage of that is now you no longer have the date and time as a bona fide date time class in R. And so if you wanted to plot these as time series, you wouldn't be able to do that as easily. So like,
Okay.
and that's part of the reasoning why I like the floor date, because you know, even though you're saying it's on the first of the month, that's not really the actual date. You can still sort of do some tricky things in ggplot to kind of make it look like it's still a time series. So if I wanted to do a time series of mean PG, I could still do that. So this is like the monthly averages for this time series. And it looks like a time series. It's not super technically correct for the data because you're still just, the first of the month for each one. That's not one of those actually collected or estimated, but you can still plot it this way. And it's just sort of useful for these follow-up exploratory analyses. You could, manipulate this SAP join data set into sort of a longer format, so you can plot both mean PG and mean chlorophyll on the same plot, or as faceted plots, and still keep that time series approach to plotting.
Okay,
And that to me is just.
Okay, no, that's helpful.
Does that make sense?
Yeah, sorry, I didn't mean to cut you off, but I'm following you. Like, I'm on the same. That made sense.
Okay. But yeah, you should give the exact same answer because you're grouping by 2 columns, and if you slice up the rows by the divisions that you defined for month and year, it should be the same ones as the floor date. So.
Cool. Sounds good. Thank you so much.
Yep. Any other questions? All right. Well, thank you all again for sticking on here, and just feel free to reach out if you have any questions.
Yeah, thank you very much. This is super helpful. Gives a lot of ideas of ways to massage the data and check things out.
Good. That's the intent.
Yeah.